Hello everybody, in this video we will discuss synthesis of epoxides. Well, epoxides can be synthesized from simple alkene like this ethene. So if you have a simple alkene and you treat them with a peroxy acids, so I will explain what is a peroxy acid in a second. So you will end up making something called epoxides, right? So this is our epoxide. If I want to draw the extended structure, so you notice there is nothing changes with carbon and hydrogen. So basically what happens is an oxygen get added on top of the double bond. All right, so that's basically our epoxide. So let's discuss what is a peroxy acids. Peroxy acids are basically carboxylic acid. So if you look at here, this is a simple carboxylic acid. However, peroxy acids is where hydrogen is replaced by another oxygens. So there was a hydrogen here before, but now that hydrogen is gone, it is replaced by OH. So that's basically a peroxy acid is. So that's our peroxy acid. So in books or questions everywhere, you will see this. So that's metachloroperoxybenzoic acid. So let's draw the structure, see if we can draw it from the name. So it is a peroxybenzoic acid. So let's draw benzoic acid first. So this is benzoic acid. Then peroxy acid would be, H would be replaced by OH. Then it says metachloro. So if you know, if you haven't known already, the bond that is right next to this bond here, so these locations are called ortho. Locations next to ortho are called meta, and the opposite, the one that is opposite, is called para. So because this is metachloro, I'm just gonna add the meta locations a chlorine group. So that's metachloroperoxybenzoic acid. Again, the name is not important. The structure is not important. What important is the reactions. So basically what we can do here is we can take an alkene, treat with the peroxy acids, and boom, we got our epoxides. Now, why epoxides are important? In epoxides, the bond angle between this bond and this bond, or this bond and this bond, is highly strained. This is a three-membered strained ring structure. So these epoxides are very reactive towards any nucleophile. They can easily be broken up into like open chain structure instead of three-membered ring structure. So that's why these are chemically important structures. Okay, so let's look at what are the other ways we can make. So let's practice few of those. So let's say you have a structure like this and you treat them with MCPBA. We will discuss stereochemistry in a second, but let's try to do the basic reaction. So we can make epoxides from double bond. So what if you have a cyclohexene? Okay, this cyclohexene looks ugly, so let's make it prettier. So let's say you have cyclohexene and you treat them with MCPBA. Obviously, we're gonna make epoxide, all right? That's our epoxides. But let's discuss a little more. What are the other technique we could use to make epoxides? So if you have remember from your organic 1, if we react this cyclohexene in presence of dichloromethane, we can have anti-bromination. So we can have brominations, right? So we can add bromine on the top here and then bromine on the bottom here. So this is an anti-brominations, right? So bromine get added on top of each other. Or what is the other molecule that you can make? Here, bromine can be added to the bottom. And so that's basically, you can make the enantiomer of each other. So basically what you can do is you can add bromine across the double bond on the opposite side. One bromine has to be on the top, another one has to be on the bottom. So you're going to have plus enantiomers. Okay. But instead of doing these reactions in dichloromethane, you can do these reactions in water. So if you do that, you will end up, so I will be consistent. So, oh, let's add OH here. It doesn't matter, but we'll use the OH there. So let's say we can do this. So where bromine gets added on the bottom, then the OH from water will be added to the top. So I will color code the bromine was red. And the opposite versions can also happen, where the OH gets added to the bottom and the bromine gets added to the top. All right, so either one can happen. So basically you can have two enantiomers making the same reaction. So this is our halohydrines. Now why this is important? So the reason I'm showing you this reaction, there is an alternate way of making the epoxides. So here is why. So this is kind of a derivative of Williamson's ether Williamson's ether synthesis reactions. So let's say I will start with here. I will use this molecule here. So what would happen if I treat them with OH minus? Okay, so if I treat them with OH minus, this proton here is an acidic proton, OH minus is a base. So we can deprotonate this. So we can deprotonate this and we will end up making an alkoxide ions, right? So we will end up making an alkoxide ion. So it's O minus. And on the here, it's Br. So here is N plus water. So we could do the same thing on the other side. So let's focus on this molecule right here. So now what will happen is your O minus is going to have a nucleophilic attack on this carbon center. Because bromine is a good leaving group, so bromine can go out. So O minus will say, yo, there is a carbon atom right there where bromine is attached and I can kick bromine out. And if you do so, you will end up making an epoxide which looks like this. So where oxygens, so this is an internal SN2 attack, right? So it's intramolecular SN2 attack. Intramolecular SN2 attack. And so from the opposite side, of the bromine. Now this is important. So this is important because bromine was to the bottom. If the bromine was to the top, this reaction is not going to be possible. So both has to be opposite in order to make this reaction happen. And this reaction will happen because when you make the halohydrin, the bromine and OH gets added on the opposite addition. So this is anti-addition of, so this is anti-additions because they added bromine and OH gets added on the opposite side of the double bond. All right, that's all we had here. So let's try to draw a couple of structures with proper stereochemistry. So if you know our alkene are sp2 hybridized, right? So alkenes are sp2 hybridized. So which means they are planar structures. So this means they are planar structures. So maybe I will draw one here. So this is a plane. Okay, so this we can have a double bond on this plane like this. So now your epoxide, when you make the epoxide, the oxygen can get added to the top like this. So, or you can add the oxygen to the bottom as well. So you can add the oxygen to the bottom side. So as a result, you're gonna have different structures. So just remember both of the possibilities can happen. If you, after adding oxygen, if you are developing a chiral center, in this particular case, let's say all of them are CH3, then you're not gonna develop any chiral center. But just in case, if you are developing a chiral center after adding epoxide, remember epoxides can be added on top and bottom. Then that might cause your next step of the reactions can have different products. All right. So let's say you want to draw something like this. How can we draw? So there is a double bond here. I'm going to add an ethyl group here. I'm going to add ethyl group here. So ethyl group are on the opposite side trans. Maybe I will add a methyl group here and I will add a hydrogen here. Okay, so you don't have to write the hydrogen. I'm just showing you all the 4 different groups. So how can you draw the product with MCPBA? All right, so let's do this. So I'm gonna number all the atoms so that you can 4, 5, 6, and there is a 7th carbon atom here. So that we will not lose track of. So first thing you want to do is draw the carbon atom 3 and 4. Okay. So you can draw the carbon atom 3 and 4 and then add an epoxide on the top. So when you draw a stereocenter, 2 lines are going to be on plane. So these 2 lines, the straight lines, are going to be on plane. Now let's draw our dash and wedges. Now every center is going to have a dash and wedges. So I'm going to add a wedge. And then I'm going to add a dash. Okay, so we got dash and wedges. So let's number our. So this is number atom 3, this is 4. Again, if you notice, carbon atom 2 and carbon atom 7 are on the same side. So these wedges are pointing towards you. So both of them have to be on the same side. So this number here is going to be 2. This is going to be your carbon atom 7. So this is your CH3. This is your CH2. Okay, I will number this in yellow 2. And this is our 7th carbon atom. All right, so that's how you do it. Remember, second atom is connected to a methyl group. So let's draw that. So here it's our methyl group. And now you see the hydrogens and 5 and 6 are on the same side. So I will put 5 and 6 are on the same side as well. So I could have hydrogen here and then CH2, CH3. So this is our 5th and 6th. So again, so the ethyl group and the methyl group are on the same side. So this is what you got. Ethyl group and methyl group on the same side. Hydrogen group and the ethyl group are on the same side as well. So that's how. So you can draw this on the opposite way, which is basically mirror image of this structure. So the mirror image can be, like if you want to draw this, maybe I will draw this here. Okay, so you don't have to add oxygen to the top. You can add oxygen to the bottom. And I will start it the exact same way. So first I'm going to draw the carbon atom 3 and 4. So that's your 3 and 4. And then you make an epoxides. So that's basically we are drawing a mirror images of this one. And draw dash and wedges. So I will draw a wedge. And I will draw a dash. All right, so we got our dash and wedges. So the mirror images of this one would be where CH3, the carbon atom 7, and 1 and 2 are going to be on the same side. So here CH3, CH2, CH3. So I'm going to number those. So you're going to be 1, 2, so this is 3, this is 4, and the 5, 6 would be here. CH2, CH3, so this is 5. This is your 5. And this is the 7. So you notice our 1 and 2 are on the same side. So this is, we are basically drawing the mirror images of this structure on this particular plane. And last thing I forgot was hydrogens right here. Okay, so you can have two structures on this one. Again, you don't need to do this way. Just know that oxygen on the epoxides can be added to the top of the double bond or on the bottom of the double bond. People don't draw like this. Usually when you draw the epoxides for problems and everything, I will show again. We always try to draw them in the same orientations to the top. And then all we do is instead of drawing them, instead of drawing oxygen 1 to the top, 1 to the bottom, all we do is we flip the group here. So, but you're still gonna maintain the same side. So if you notice, CH3 was to the top, to the in the wedge. So I'm gonna put the CH3 on the dash this time, and then CH2, CH3, this one on the top, on the wedge, sorry, on the wedge, yeah. And on this side, I will do the same. I will put the CH2, CH3 on the dash, and I will put the hydrogen on the wedge. So there we go. So we got our hydrogens here. Before it was dash, now it is wedge. The ethyl group, which was dash before, now it's on the wedge, but they're still to the same side. So if you notice, this was dash to the dash, now they're wedge to the wedge. They're on the same side, but they just flipped, different stereochemistry. And same thing can be drawn here. Okay, so you notice they are still to the same side. They are now dash dash. Before they were wedge wedge. So that's how you can draw both of the structure. So it doesn't matter what you do, which structure you do, you can just say this plus enantiomers. But key point that you want to keep in mind is carbon atom 1 and 2 should be on the same side of 7. Hydrogen should be on the same side as 5 and 6. Okay, so there are a couple of different ways. So you can make epoxides either MCPBA or using halohydrin as well. And you can draw the stereochemistry. All right, so in the next video, we will talk about reactions of epoxide, which is ring opening structures. All right, let's stop here.